Okay, let's go over, now we're going to go over MPLS traffic engineering. And depending on the time, we can go over endless examples with traffic engineering. In fact, traffic engineering could be a class upon itself if it really, if someone was really interested in it. One of the issues that we run into with traffic engineering with preparation for the SP lab is that there's a lot of features, a lot of enhancements to traffic engineering that just are not supported by the iOS versions that we are using. There's a lot of really advanced features that pretty much very few networks use unless they're really large scale. So what we're going to focus on is on core traffic engineering configuration and verification and a little bit of troubleshooting there. And we'll look at using traffic engineering for MPLS VPNs as opposed to using BGP or LDP for label distribution. First off, what is traffic engineering? This is taken right from the RFC. The whole idea is we're trying to optimize the network to get the best possible utilization of the available bandwidth that we have. We'll see some limitations with IGP protocols and how they allocate, not allocate bandwidth, but how they choose paths through the network. So the whole idea is we're going to try to optimize the utilization of the bandwidth in there. So what problem does it solve? Well, like the RFC said, efficient use of all available bandwidth. Help ensure that the desired path through the network is selected and used. Okay, so, and we also want to, another idea is cost savings. All right, so we want to try to use up, as much of the available bandwidth as possible before we switch over and have to add new physical links, new PVCs, new frame relay DLCs there. So the idea would be to look at the network, find out where there is available bandwidth, and then engineer your traffic so that it utilizes that available bandwidth. Okay, so the issues, well, some people say, well, why don't I just do this with OSPF? I'll get in here and start manipulating the metrics. It's hard with OSPF, or pretty not impossible. I mean, pretty much very few things in networking is impossible. But you're going to be hard pressed to make even something like EIGRP truly use maybe 20 megabits on one link, 10 megabits on another link, and so forth there. You do have variance, but if you get into some really big, large-scale networks, and I've worked on some pretty large EIGRP networks that eventually switched over to like the OSPF or ISDIS so that they supported traffic engineering. Even with variance, you really can't do a lot. You can do some basic things with variance, but you really can't get into a lot of quote-unquote traffic engineering with it. Okay, so the protocols that we're going to deal with here, the common ones we see in MPLS network in the core are OSPF and ISDIS. The problem that we run into with these routing protocols is that they select the path to the destination. They'll select the least cost path. Okay, and then they put that least cost path in. If I have 6 possible paths, let's say I have a 60 meg link, a 50 meg link, a 40, 30, 20, and 10 meg link, OSPF and ISDIS are going to select the 60 meg link. But yet I have left over a 50 meg link, a 40 meg link, a 30 meg link, and so forth there. So there's available bandwidth left over that I would definitely want to utilize. So IGPs, OSPF, and ISDIS really can't get in there and say, okay, let's send 10% of the traffic this way, 30% of the traffic this way, and so forth there. Okay, we could get in there, like we said, try to manipulate some of the metrics, but that's really not going to work. You can alter some paths, but the problem is, as soon as we alter the path, we just switch the problem somewhere else. We can't get in there and say, if the cost is 10, use this link for 10 megabytes. If the cost is 20, use this link, send 20 megs of traffic across this link. You really can't get in and do that. It's either this link or that link, or if they're identical, it's both links. Okay, so we all know how IGP routing works. We all know the issues we can run into. And like I said, it doesn't have that ability to really get in there and fine tune. It doesn't have that granularity to get in there and fine tune that there. Well, another thing, even though technically OSPF supports type of service routing, which Cisco never implemented, we may want to route based on QoS. So we want to route traffic based on QoS. We want to say anything with this MPLS EXP bit set goes across this path of the network. Anything with this other bit set goes across this other path in the network there. All right, so these are the issues that we run into here with using IGPs to try to do any traffic engineering. So let's look at this here. Let's say we wanted to send traffic from, let's say we're going to send traffic from R8 over to R7 here. Now we have different paths in the network. Of course, we have the network designed like this for cost-saving reasons, right? Only kind of weird-looking design here. So we got this design here, and if we look at it, so let's say that this link here, let's say that this link here is a gig. This link here is a gig. This link over here is a gig here. Down here, and we'll look. All right. So these links are all gig here, and I want to use, if you look at like OSPF, well, what path is OSPF going to select? Well, it's going to select the direct connection. When it goes from traffic goes from 8 to 7, it's going to select that direct connect there, assuming we didn't manipulate the metrics or the cost in any way, shape, or form. We left it to the default. So we have this gig link here, and let's say it's, this is, of this gig link, we have, let's say of this gig link here, path we take, let me draw the path we're going to take here real quick. Let me draw the path we're going to take. I'll remove all those off. We'll just say all these are gig links. Okay. All right. So this is the path we're going to take. We'll just say all the Ethernets are gig for simplicity's sake here. The path we would take here is not maybe the path that we really want the traffic to use. Maybe for whatever reasons we want traffic to go down a different link. Let's switch that over and let's just say this link here is a fast Ethernet. So this is a fast Ethernet link here. This is a fast Ethernet link down here, and let's just say this one over here is a gig link. I'd write it on the board there. There we go. So that's a gig link here. So let's say we have a service contract to send 120 megs of traffic, or allow 120 megs of traffic between the sites of R7 and R8, behind R7 and R8. This is going to be a little tough here, right? With like OSPF. I mean, how are we really going to do that? Well, with OSPF, what we could do, manipulate the metrics so this looks equal cost and it load balances across the two possible paths there, which is fine as long as that link, as long as there's enough bandwidth there. But what if we switched this here? So this was not a gig link here. This was just a regular Ethernet link. Okay, and let's say the requirement was to send the maximum we could possibly serve out is 110 megs here. So it was 110 megs. So now how would we do this with like OSPF? Be pretty tough. Because what we need to do is send essentially 10 packets, theoretically 10 packets this direction for every 1 packet this direction. Okay, really is not a, as you see with OSPF, really won't work. Just as a side note, stupid router trick kind of stuff. I haven't seen it on this scale. One thing you could do, this weird load balancing with static routes. The way you would do it with static routes is you would have to put a primary IP address on this interface here between R3 and R6. You would have to put 9 secondary IP addresses on, and then what you would have is 10 static routes. You'd have 10 static routes on R6 pointing. First one points to the primary IP, second one points to the secondary IP, and so forth there. Then you would put 1 static route pointing down to 5 here. We're talking about static routes pointing to the same destination. So let's say the 10 network. Okay, in this problem, you'd run into in this situation, you'd run into real problems because of the limitation of the iOS of how many multiple equal cost paths it can have. But if you look at it from if we look at it from a a serial link perspective, you may just send you may just send 2 packets between 3 and 6, and then 1 packet between 5 and 6. It's just kind of it's not a real, you don't see it too often in the real world anymore, but it's more of a people talk about what protocols support load balancing. Then you jokingly say, well, the static routing protocol. I like to jokingly call it the static routing protocol. That supports also load balancing too. It even supports unequal cost load balancing, and the way you do it is add those secondaries on there. Just as a side note there. But we can all see the issues with using traditional routing there. Okay. Traffic engineering is going to use RSVP. So it is going to use RSVP to establish those LSPs. Before, when we were looking at, before in the class, we've used LDP to establish the link state paths. Label switch paths, I don't know why I want to call it link state path. In fact, when I was looking at these slides earlier, I said, I'm going to call that link state path. It's label state path here. Label switch path. Man, this is kicking my butt here. Label switch path. The problem with RSVP, though, the problem that we have with it, though, is it's a host-to-host protocol, meaning that a host would signal to another host if there's available bandwidth. If there's available bandwidth in the network, as you can imagine, you really wouldn't want all the hosts in your network signaling to each other about, hey, is there such and such bandwidth available in the network? Imagine all the utilization on the routers. So it never really took off. So we're going to use extensions that are added onto RSVP for our LSPs. All right. Additional features that we get out of using RSVP, one of the big ones that we're going to get out of here is explicit path configuration. In essence, it'll be traffic engineering. Okay, so we'll know the exact path we want to take through the network, or we may want to know just a possible path through the network, meaning that I don't want to know the exact path. I just want to know that I crossed these 2 routers in my transit across the network there. So let's look at this here. So let's say we have a tunnel, traffic engineering tunnel between R8 and R7. The IGP path would prefer, obviously, the link here, assuming that the Ethernet links are all the same here. So, but for whatever reason, we want traffic engineering to choose the path of from R8 to R6 to R5 to R1 to R3, and then finally to R7. So once we have it configured, what we're going to have is based on our requirements, R8 is going to send out a path message. R6 is going to get it and send out a path message. That path message is going to essentially go all the way across here. R5 is going to send out a path message. So it's essentially we're going to signal all the way across over there to R7. And once we get to R7, R7 is going to send back the reservation. So this particular path and this bandwidth has been reserved for this here. But it's also for us with traffic engineering, it's going to send a label. So what you're going to have is for this particular destination here, what you're going to have is R7 is going to send to R3 the label of, it's going to say pop. It's going to say pop the label. Then R3 is going to send the label to R1. This label will be whatever the value it chooses. So 23. R1 sends the reservation and the label across to 5 to reach this destination. So then it's built back all the way up to R8 there. So RSVP will build these labels for us here. And we'll look at it just like what we looked at earlier when we were using LDP. Just show MPLS forwarding to look at our labels there. Of course, there's some additional commands relate to MPLS that we'll look at here. MPLS traffic engineering, I should say. Traffic engineering, how does it determine the path it should take? Okay, so how do we determine the path we should take through the network? Commonly what you see is people who have an explicitly defined path through the network. They say, I want to take this path through the network. So I want to go from this router to the next router, then to this next router, and then from that point I really don't care. Or I want to go between my source and destination, or I should say from my tunnel head to the tail of my tunnel. I want to go between, I don't care what path I take through the network as long as I hop across these 2 or 3 routers. So you can specify it, be it strict in the fact that you specify the exact path you take. You could specify it loose, meaning that I'm not really too concerned the exact path. I just want to cross these particular nodes between that the tunnel head and the tail of the tunnel there. The administrative weight is an option too. By default, the administrative weight, if our tunnels are built dynamically, by default the administrative weight is based off of the routing protocol's cost. So the metric used for that link there. We could also have restrictions on the bandwidth, meaning that whatever path I take, I want to make sure that my that this path supports 10 megabytes of traffic or supports 50 megs of traffic. So we can do this restriction. The path we take through the network is constrained, meaning that it is we will still do an SPF on it, but it is constrained, meaning we have additional restrictions on it. This is different than, as you can imagine, with like OSPF. We don't take this consideration in with OSPF. We don't take available bandwidth or anything like that with OSPF. This can get really complicated in big networks. Specifying the path that your traffic's going to take between one customer's VPN sites. It can get really complicated. Commonly what's done is this is done offline, meaning that someone's got an application, they sit there, they look at the bandwidth that's available in the network, and then they re-engineer the paths through the network based on the bandwidth that's available. The hardest part of traffic engineering in the real world is figuring out what is your bandwidth availability. How much bandwidth do you really have available all the time there? So this path calculation here, like I said, it's really tough in a big network to get in here and try to do this on the fly, meaning that to jump on the routers and do this configuration. Most large-scale networks, this is offline. This is done offline with an application, like an application from Cisco, that'll do this path calculation for you, and then it'll set up the RSVP traffic engineer tunnels for you automatically. Okay, obviously for us, we're going to need to do this, based on our requirements. We're not going to have an offline tool, obviously. Okay, traffic engineering is going to use OSPF or IS to IS. Okay, it's going to use the type 10 LSAs, and look at the term here, it's area local. These are area local LSAs. So this is going to mean that our traffic engineering configuration is restricted to a single area. Okay, it is restricted to a single area here. Now there's a lot of talk, about support for inter-AS traffic engineering or inter-area traffic engineering. The iOSs that we use do not support that. So if we're going to do a large-scale traffic engineering design, more than likely it'll be one big area. This is why you see sometimes you'll see ISPs say, well, you know, we really like to use IS to IS over OSPF. Because with OSPF, you do traffic engineering, at least in the case of a lot of the iOSs out there today, you can't do inter-area traffic engineering. You're stuck to one big area. Okay, so you'll see that IS to IS tends to scale better using, you know, one big flat area there. Okay. So if we're going to do traffic engineering here in the iOS that we have, we are going to have to constrain it to a particular area. With IS to IS, you're going to specify, you're going to configure the routing protocol to support these extensions, these TLVs, type length values here, and we're going to specify, is it going to be level 1 or level 2 traffic engineering? And you could do one or the other. All right. So the extensions that we add is we're adding the ability to disseminate information about the available bandwidth. Normally, when we're doing an SPF calculation, we want to know information, of course, about ourselves. We want to know information about the neighbors, who our neighbors are, and we want to know the cost to these neighbors. If I have all that information and I have the neighbor's information about its neighbors, so it's our neighbor's neighbor here, I'm able to build an SPF. I'm able to run the SPF algorithm to figure out the shortest path first, the results here. Traffic engineering is going to add in the addition of getting the available bandwidth for traffic engineering there. So we're not only going to know about the neighbor and then the cost of neighbor, we're also going to know about the available bandwidth there. When we get onto the routers here, the command we're going to use to verify what's going on in the network, what interfaces are supported, and who sees who is a show MPLS traffic engineering topology. This will show us everything about the routers that see, essentially, even if you don't configure a lot, you can still do a show MPLS traffic engineering topology, even if you don't have a bunch of tunnels configurations. It'll show you, it'll show you who your neighbors are, who your neighbors' neighbors are, what their IP addresses are, what their reservations that they have currently, what their available reservations are, and so forth there. So it builds this when it first starts to set up, when we first start to set up MPLS traffic engineering, it'll build this topology either using OSPF or using IS to IS. The commands under the routing process. So the commands under the routing process here. We're going to need to specify MPLS traffic engineering and then the area ID. If you specify an area, if you specify one area, you can't, there is some examples you may see on CCO where they've got this command applied twice. In the iOSs that we're using, you can't apply this command twice. Okay, and it's done for inter-area traffic engineering with OSPF. With the iOS we're using, it's only a single area. Then we also need the router ID. So this is the router ID, and this should actually say the interface here. So this is the interface here. When you're doing MPLS VPNs and you're doing these large network stuff, always make sure everything chooses the same router ID. Okay, don't say, well, I'll use this router ID for BGP, and then I'll use a different router ID for OSPF, and then, you know what, I'll give traffic engineering its own router ID. Don't do it. Okay. For IS to IS, the first thing we need to do is set the metric style to wide. We need to support essentially, we need to support wide metrics here. Okay, by default, the metric style is narrow. Then we need to specify the MPLS traffic engineering level. Essentially, is it going to be level 1, level 2? If I'm only running level 2 in my network, of course, I'm going to specify level 2. If I'm only running level 1, of course, I'm only going to specify level 1. They're pretty straightforward. And then, of course, the MPLS traffic engineering router ID, and then the interface there. The thing to remember, too, when you start configuring MPLS traffic engineering, you can run into some weird problems with order of operations, meaning you configure everything for traffic engineering, but forget to enable support for the IGP. You should enable support for the IGP first. So do this first before you actually go in there and start configuring traffic engineering. And by configuring traffic engineering, I'm referring to the commands we'll go over in a minute relating to the ones created to the tunnel and the interface and so forth there. So enable support for it first, then go ahead and apply your configuration. You can, like I said, you can run into really weird problems where you end up having to reload the router because you configured everything with traffic engineering but didn't enable support for it within your IGP. And currently, as a side note, because, like we said with, let me jump back a couple slides here real quick. Go back to the slide where we talked about, actually it's right there. So we're doing constraint-based shortest path first. SPF implies what? Implies a link state protocol. So the link state protocols that we have available to us are IS to IS and OSPF. We can't do traffic engineering with EIGRP. Okay, the different options we have for selecting the path. We can choose dynamic or we can choose explicit. Dynamic means the routing protocol we're using, IS, IS, or OSPF, will select the best path through the network from the head of the tunnel to the tail of the tunnel. Okay, which is essentially, you'll find out that the best path is also the same path for your unicast routing. So you may want, commonly what you'll do is do an explicit path, I should say. So you'll get in here and do an explicit path rather than doing a dynamic path. It's good, of course, preparing for the SP lab to know both. We want to know both. But not too many people use a dynamic path. You can, the implementations that you see out there using dynamic paths, by default, when traffic engineering tries to determine the best path through the network, it uses what's called a weight. That weight is based off of the IGP metric for the link. So it's going to choose the least, weighted or the least cost path, the one with the least weight there. So what you can do is get in there and configure for an interface in administrative weight, so that you can so that the traffic engineering tunnels can route themselves around the network dynamically, but they're not going to be based. They're not going to route based on the the OSPF path or the IS to IS path, because if you leave it to the default, they will both select. The tunnel will select both the IS to IS path, whatever it's using, or the OSPF path, whatever it's using there. But like I said, commonly is explicit, the explicit path there. Other constraints too, there may not be enough bandwidth in the path that you select, so it may try another path through the network there. You can have multiple path options, meaning you can have an explicit path. If that explicit path isn't available for whatever reason, you can fall over to a dynamic path. You can have, a cascade of explicit paths. You could say, I want to go exactly this path. If you can't set up my tunnel exactly this path, well then try this other path. And if you can't try the third path, and if you can't do that, try a dynamic path there. So we can specify more than one, and they can both be used together in the same tunnel. One important thing to note, traffic engineering tunnels are unidirectional. So you set up traffic, you set up a tunnel from the head to the tail. That's the flow of the traffic. When it comes back, it doesn't come from the tail to the head. It goes out across the network normally. So they're unidirectional there. So you're going to have, if you want traffic to flow, between two routers, a certain path, between source and destination, both ways, you're going to have to set up two tunnels. You want to go on the head router, set it up to the tail. Then on that tail router from the other tunnel's perspective, you're going to make a new tunnel, which makes it a head for that tunnel, and then point down to the other router there. So they are unidirectional. It makes looking at the label switch path a little tricky because you're not seeing the return label. You're only seeing, not the return label, but you're only seeing the path set up in one direction. Normally, when you look at the LFIB or the MPLS forwarding table, you're seeing your local label and the remote label. With traffic engineering, you're not going to see that because it is unidirectional. Okay. All right, and the commands we have here, and these will be under the tunnel we configure. There'll be some more commands we'll look at here in a minute here. We'll specify the bandwidth. So this will be the bandwidth that we want. So this tunnel wants, 100, not 100, but probably 10 megs of bandwidth or 50 megs of bandwidth there. We can also specify a priority for a tunnel. We'll talk about that here in a second here. The path option. This is what we were referring to earlier. The path option here. So the path option, the number, the lower the number, the more preferred the path option is. Specify it's dynamic or it's an explicit path through the network here. If it's an explicit path, we need to specify the name of the explicit path that we created. Or we can also specify the ID. It's just a numeric value. It's one or the other. We can also do what's called lockdown so that it doesn't re-optimize itself. Every now and then traffic engineering is going to try to re-optimize itself in the network there. So it's going to try to re-optimize itself so that it sees that if there is, it looks to see if there is a better path through the network than when it really was set up. Okay, the priority here, MPLS traffic engineering priority here, the setup priority and the hold priority. The setup priority says, what is your priority to set up your path? Meaning that, can you possibly override somebody else's reservation that's already existing in the network? Your hold priority says, what is my priority to hold this path, up here? So the common configuration you'll see is, like for a practice lab type scenario, you'll set this to like 0, 0. you'll just say MPLS, under the tunnel MPLS traffic engineering priority 00. That's the best possible priority there. If you have two tunnels and they both say 00, they will both have equal access to that particular available bandwidth there. Now, if somebody's setup priority is higher than somebody else's hold priority that the tunnel is already up, you would preempt that tunnel. So you will essentially take down that tunnel that is already up there. So that's the basic idea. Once I'm, what is my setup priority? Usually you set this something fairly high. You got 0 through 7. So you'll set this high to like 7, meaning that I don't really want to preempt anybody who's already up. Okay, I may have a class of traffic that I always preempt no matter what. So this is like some customer that's doing transit, and it's like low-end type of sale. I mean, you're really not charging this customer a lot for the transit. So then what's going to happen is your customers that are paying, you're going to allow them to come in and tear down their existing reservations for this other customer who's not paying much, and create a reservation on top of that. Well, I should say in place of that there. So normally your setup priority will be higher than your hold priority. If you want your tunnel to stay up once it's already built and traffic's flowing across it, you'll just set the hold priority to 0. If you want possibly the tunnel to be preempted, you just set the hold priority up. Okay, commonly you see values in a real network something along the lines of, most people don't go to the extreme of 7 and 0 because it doesn't give you any way to grow or work around it. Most people go like 6 and 1. So the setup priority will be 6, the hold priority will be 1. Okay, and then it allows you to go in there, and if you really got this, if I really got this customer that really needs this traffic through the network, I can give that a setup priority of something below 6, and then I could give it a hold priority of 0 there. So that's the basic logic. The best possible to have is 0, 0. The worst possible to have is 7, 7. Okay, the path option here, we talked about here. The path option, this is a numeric value from 1 to 1,000. Okay, so it's a numeric value from 1 to 1,000 here. We can have multiple path options through the network here. The explicit path, here, this is commonly what you see in real-world implementations. Commonly what you see in real-world implementations. Not the only thing you see, but common. So we'll specify the explicit path, specify the name of the explicit path or the identifier, and then enable this explicit path. You could disable this path, meaning don't take this path. So what I'll have is I'll have a explicit path that's a disable path. I don't want you to take this path through the network. All right, so commonly what you'll do though is you'll specify, what is the next address I'm going to hop to get there. So I'm going to specify the next address to get there, and then hit enter, and then go to the next address, then go to the next address, and then on down through the network there. And this, of course, will be bound under the tunnel interface. But these are the constraints. The reason I show these are the constraints that make up constraint-based SPF. Okay, so we're doing SPF, but we have additional constraints on it here. All right. Now that our tunnel is actually built, not now, but once our tunnel is actually built, how do we route across it? So how do we route across the tunnel? Okay, so what we're going to do is we're going to do static routes. So we're going to configure a static route pointing down the tunnel. We're going to do policy-based routing to policy route traffic through the tunnel. We could also do dynamic routing. So we could essentially have the the IGP that we're using, either IS to IS or OSPF, we can have it announce the tunnel. Now, they don't actually run across the tunnel. They just announce the tunnel there. So they announce the tunnel in IGP. This is pretty much a common solution to announce the tunnel. And we'll look at both of these as options here. And once again, this command will be under the tunnel interface. You see, obviously, all the commands that start with tunnel relate to the tunnel interface. Every command we've looked at before that was MPLS related, except for the ones with the routing protocol, all go under the tunnel themselves. Okay, basic steps for configuring, for essentially enabling, I should say, traffic engineering. So the basic steps we want to go through: ensure Ceph is enabled. Don't assume that Ceph is enabled. Don't assume that it's always enabled and you'll never be on a router that somebody did not disable Ceph for. Make sure Ceph is enabled. Enable traffic engineering support for the protocol. That's what we did earlier when we talked about under the OSPF process or the IS to IS process. The next step is in the global configuration. We need to specify MPLS traffic engineering. We need to specify MPLS traffic engineering tunnels. So this tells us that we're going to do traffic engineering tunnels. Once we have that done, we're going to do the same command under the interfaces where we want to run traffic engineering. Okay, the last command we're going to do is we're going to specify the bandwidth for that interface. Now, this bandwidth may or may not relate to the real bandwidth of the interface. We may have a 100 meg link, but yet we are going to, we're going to only use 50 megs of it for traffic engineering. So it may or may not relate to the real bandwidth of the interface. So you're going to say IP RSVP bandwidth under the interface, specify the total bandwidth available for traffic engineering, and then you can also specify a per flow. So I could say there's 100 megs available. Per flow, the maximum I will allow is 20 megs. So I could have a maximum of 5. I could have not a maximum of 5. I could have a lot more than that, but I could have 5 reservations of 20 meg each. I could have 10 reservations of 10 megs each, but I couldn't have 1 reservation of 100 megs. But if I went under the interface and just said IP RSVP, and I specified 100 megs here, and hit enter, it would allow 1 reservation to take up all that interface's bandwidth there. If you don't specify it, so if you don't specify the IP RSV bandwidth, and if you just hit enter, IP RSV bandwidth here, it's going to default just like normal QoS. It's 75% of the interface's bandwidth. Traffic engineering is only concerned with the IP interface, meaning that it's not going to, if you're doing sub-interfaces, you're not going to go up to the main interface and figure out what its bandwidth is. You're going to use whatever you have under that sub-interfaces. Commonly, in the real world, you don't see a lot of traffic engineering on sub-interfaces. A lot of people running GigE or packet over SONET interfaces. You don't see a lot of sub-interfaces in the real world. But if you do have to do traffic engineering on the sub-interfaces, it's based off that sub-interface's bandwidth there. There's nothing you need to do to the physical interface for traffic engineering if you're doing sub-interfaces here. If you don't specify the IPRSP bandwidth command, you're going to essentially have a bandwidth set to 0, meaning that nothing can run across this here. Okay, traffic engineer will still work across the link. There will still be signaling, and there will still be advertisement of labels, but there's not going to be any bandwidth available to go across that link. So it's more of a misconfiguration than an actual option. But it can be misleading when you start to do troubleshooting and you start looking at your topology and you're trying to figure out what the problem is. So every router will have, you know, every router that you do traffic engineering on, and these could be the tail router, that could be head-in router, this could be the routers in the midpoint. Every router you're going to have to enable Ceph. You're going to have to enable traffic engineering support under the link state protocol that you've used in your network. You've got to enable traffic engineering globally. You've got to enable under the interface, and you have to specify IP RSD bandwidth there under each interface. These are the things that you should be able to remember. Even if you're not an expert with traffic engineering, you should remember this part right here. This is the basics that you're going to put on every router in the network that is going to do traffic engineering. If you leave some of this stuff off, traffic engineering is not easy to troubleshoot. Okay, it is not easy to troubleshoot at all. You really don't get a lot of really intuitive error messages. Okay, you can do some in-depth troubleshooting to help kind of diagnose what the problem is, but the error messages that you see or the output from the show commands are just not very intuitive. And we'll look at that here. So these are the basic steps here, the basic steps that you want to go through for every router. Okay, so let's look at the topology that we're going to do, and then we'll look at the full configuration here. So the topology that we're going to use is we are going to enable traffic engineering between R3 and R5. So between R3 and between R5 here. So we're going to enable traffic engineering here. Okay, so R3 and the traffic engineering is going to be in the direction of from R3 to R5. It's unidirectional. So what we're going to do is we're going to make a GRE tunnel, not a GRE tunnel, we're going to make a tunnel on R3. We're going to specify that its mode is MPLS traffic engineering. Then we're going to specify the destination is R5's loopback. There's some additional commands we may want to set up, and we'll look at those here. And then that's pretty much basically it, assuming that we've enabled those steps in the previous slide. That's pretty much it. We don't do anything on R5. We don't do anything on R1 as far as creating the tunnel is concerned there. All right. So let's look at the configuration. This is done in the globe. Let me change this to yellow real quick here. So in the global configuration, MPLS traffic engineering tunnels. We're going to the interfaces first. Enable support for traffic engineering tunnels. Specify IP RSD bandwidth here. Okay, in this example, I didn't specify any bandwidth here. Go into the routing process. MPLS traffic engineering router ID loopback. MPLS traffic engineering area 0. In this example from here, this is area 0. This is OSPF area 0 here. Once we have that done, we can go ahead and start configuring traffic engineering. What I would highly recommend, actually, before you put on the tunnel, before you actually go here and put on this tunnel here, what I recommend is you go to the midpoint routers and the tail router and configure those basic steps to support traffic engineering. You don't want traffic engineering to try to set up the tunnel prior to it being fully supported in your network. You want to eliminate as many possible problems as you can, and this is one of them. Will it always cause you a problem? No. Will it cause you a problem sometimes? Yes. Do you want it to possibly happen to you in the CCA lab? No. So what we'll do is we'll do these commands highlighted in yellow first. Then we will go to the midpoint. In this case, this is a R1. If we look at the diagram real quick, R1 is just a router in the path here. So the exact same config, MPLS traffic engineering and the traffic engineering tunnels in the global config. Then we want to specify, grab the highlighter here. Then under the interfaces, then IP/RSVP bandwidth, and of course under all the interfaces in the path, and of course enable it in the global configure. Under the routing process here. Now, as a side note, a few of these interfaces like we use in our labs, some of them are pretty slow. Like R3 serials, that's just it's a slow speed serial, so it defaults to 128K, which means 75% of 128K is something like 98K of available bandwidth. If you just say IP/RSP bandwidth here, and then you go and specify that your reservation wants 2 megs, your reservations will never be set up. Okay, so just be aware of that. In the example that we're going to do here first, I didn't specify a bandwidth. So I didn't specify a bandwidth for the traffic engineering tunnel. It'll come up. It won't require a bandwidth. It'll just come up and start working. Okay, not a very common solution, obviously. All right, and then on R5, it's the exact same thing. This is the interface connected to R2. So enable MPLS traffic engineering tunnels and global config. If you try to do it under the interface, it'll kick off an error if you haven't done it in the global config yet. All right, same thing here. Just once we have this done, we can jump back to R3. Let's go back to R3 here. Oops, almost too far there. Go back to R3 here, and let's look at the rest of the config. So the rest of the config, I'm specifying IP unnumbered. So IP unnumbered here. My destination, that's R5's loopback. That is the destination of the tunnel. And I specify the tunnel mode as MPLS traffic engineering. So, normally we specify that, it's by default, it's like a GRE tunnel or a IP and IP tunnel or whatever we're going to use. This is specifying that it is a MPLS traffic engineering tunnel. The only option we really need in here is to specify the path option. The only additional command we need in here is the path option. This is the simplest possible config. This is the simplest possible config you can really apply here to get traffic engineering up and work. And you want to know the simplest minimal config. Why? Because if you're asked to configure traffic engineering between 2 devices, and there are all kinds of requirements on this traffic engineering, what you want to be able to do is get the basic traffic engineering up. Then you can start applying and start, fine-tuning your traffic engineering configuration. But first, make sure it comes up and works. It's just like your BGP configuration. The first thing you do is you bring up your BGP peers. You bring them up, show IP BGP summary, make sure they're up. Now that they're up, I'll start doing my BGP config. It's the exact same thing with traffic engineering. Get your traffic engineering up, the basic part up, then go ahead and start putting on your additional configuration. First things first is enabling traffic engineering support within your network, and those were the commands I listed there. It'll save you a lot of headaches, believe me. A lot of headaches. There's nothing worse than having to sit and wait and waiting for traffic engineering to eventually decide it's going to bring itself up. And it can happen to you. It can sit there for 15, 20 minutes and not come up. All of a sudden, bang, it comes up. Starts working there. All right, so what we're going to do is, in this case here, we have OSPF enabled. So OSPF has been enabled here. And the loopbacks on the routers is 150.1.x.x/32. So R3 is going to create a tunnel to R5, and R3 is going to create that tunnel sourcing off its loopback there. All right, so let's look at the configuration here. Close this down. All right, let me share out my window real quick. Okay, everybody should be able to see my secure CRT window here. So what we're going to do, R3, R1, R5 is the path. Okay, so first thing we'll do is we will ping 150.1.5.5 source LO0. I can ping from loopback to loopback. So that's the first thing we do. The next thing we're going to do is enable support for traffic engineering. So we're going to say MPLS, traffic engineering tunnels in the global configuration. We're going to go under the interface that's connected to R1. In this case, it's S1/2. We're going to specify the command again, MPLS traffic engineering tunnels. Actually, I should go ahead and enable it under the routing process too. We're running OSPF here. So I'm going to say MPLS traffic engineering, and then we want to specify area 0, and then specify a router ID. And this is the loopback here. All right, with OSPF, I haven't ran into too many problems with the order of operations. IS-to-IS is the one that's really touchy, especially if you start saying I'm going to do traffic engineering for level 2, and then later on you get down to a situation where you've got to change it to level 1, and then it's time to change it and reload the router time. So your link changes from a level 2 link to a level 1 link there. Okay, so I enabled it under the routing process. So it's enabled under the routing process. Under the interface, I have configured MPLS traffic engineering tunnels. And I've also done that in the global configuration. Now what I'm going to do is I'm going to go into the interface, say IP RSVP bandwidth here, and specify the bandwidth here. Now this bandwidth, of course, is unidirectional, meaning that bandwidth could look different depending on the direction you're going. So if I'm coming from 3 to 5, it may look like there's only 5 megs of reservable bandwidth. But if I'm going from 5 to 3, there may be 30 megs of reservable bandwidth. And that's really common in an ISP type of an environment where you don't give 30 megs in, 30 megs out. It's usually not needed. It's usually your inbound traffic, your outbound traffic from your ISP is usually it's some 8-to-1 ratio, 10-to-1 ratio there, depending on really what you're doing. Okay, so we'll specify the bandwidth here, and this is in K. So so if we want to specify 10 megs or 100 megs, whatever we want to specify here, doesn't really matter. We can exceed what the interface really supports here. All right, be careful in the lab, as a lot of you guys know who have already been to the CCA lab. Be careful when you put in values in any sort of command that takes either bits, bytes, whatever it takes there. So make sure that you look to see what it takes first. It can never hurt to be 100% sure too. Show, if you do like a do show int E0/0, this is a 10 meg interface. Let's scroll up here real quick here. And we can see that's 10 megs, so that should be 10 megs. Okay, so you can never be too careful. All right, and there's little stuff like that. You'd be amazed at the people who, I do a lot of grading in mock labs for like RNS. You'd be amazed at the people who just miss something small, like they put the value, they missed a 0 on it or something like that, or it's in bits, they put it in bytes, or vice versa. Little things like that. It's not what you want to have to retake the lab for. Okay, so let's look at our configuration so far in R3. So traffic engineering tunnels has been enabled globally. It's needed. Under the interface where I'm going to do my signaling for traffic engineering. So under the interface, I'm going to do my signaling for traffic engineering, specify MPLS traffic engineering tunnels, and IP RSVP bandwidth, and then specify the bandwidth. I didn't specify a per flow bandwidth or anything like that. I just specified bandwidth here. This is what's available. Either one reservation takes it all, or you have 10,000 reservations taking 1K each. Let's look at the configuration under the routing process. Specify MPLS traffic engineering router ID, MPLS traffic engineering area 0. This is the area we have here. Pretty straightforward, nothing fancy. We're just enabling support for MPLS traffic engineering. So let's go down to R1. R1 is a router in the path here. We enable OSPF, so MPLS traffic engineering router ID, loopback, MPLS, and specify the area. Area 0 here. Then we need to enable MPLS traffic engineering globally. And then also under the interfaces here. And under fast Ethernet between R1 and R5. Okay. We have the full configuration here. I already know for my routers here when I preloaded them that Ceph is enabled here. Okay. Let's go over to 5 here. And router OSPF 1, MPLS traffic engineering area 0, MPLS traffic engineering router ID. Okay, and let's go enable it globally. Traffic engineering tunnels, and we'll go into the interface. This is the interface connected to R1, and then IP, RSVP, bandwidth, and specify the bandwidth here. Do 10 megs here. Back to 1, did I specify the bandwidth on those interfaces on 1? Show run int s2/1. Let me look, see if I specified the bandwidth there. No, I didn't specify the bandwidth there. What this would have caused is this would have caused traffic engineering to come up. Traffic engineering to try to come up, but your tunnel would never come up. All right, MPLS traffic engineering. That's enabled. IP, RSVP, bandwidth. And then also here. Okay. All right, so let's look at back here. Okay, so show MPLS traffic engineering topology. What we're viewing here is our topology of our network as far as traffic engineering is concerned. So the neighbor, we're on R3, the neighbor's R1. Okay, R1 is a neighbor to R3, which is us. I can see what is the TE metric here, and this is also called when you do under the command. If you do the command to manipulate this, it's called administrative weight rather than call it TE metric. It defaults to the IGP metric, and the physical bandwidth of the link it's a T1, but the max reservable bandwidth is 10 megs. Really good T1. All right, we are It is neighbored with this router right here. It is neighbored with R3 through this IP address right there. So it's the full topology. It's showing you the router ID, the interfaces that has it enabled, and also showing who the neighbors are on those interfaces there. So here's another link on R1. This is its link to R5. So the interface that R1 is neighbored with is .1, and it's neighboring over with .5 there. And it shows you what the bandwidth is here. It also shows you if there's any bandwidth already being reserved. So is there any bandwidth that's already been reserved here? So this shows us that we see all our routers in our MPLS traffic engineering topology. We see them here. We see the links also. So the next thing this command's used a lot in a network where you're trying to determine what reservations are already active and so forth there too. But it's really good for troubleshooting to see, okay, do these routers see these other routers, and does my neighbor see my neighbor's neighbor, and so forth right there. All right. So let's go ahead and enable. Let's go ahead and enable traffic engineering. So we'll go on to, well, sorry, it's already been enabled. Let's configure the tunnel, I should say. So we're going to say IP unnumbered and tunnel destination. This will be R5's loopback. Then we want to specify the mode here. We want to specify the mode. So we're going to say tunnel mode MPLS traffic engineering. This is saying this tunnel is an MPLS traffic engineer tunnel. Then we want to specify the path option. So that was the only other command that was necessary for us. So we're going to say tunnel MPLS traffic engineering, and all these commands start with tunnel MPLS traffic engineering, which makes them kind of long, but kind of easy to remember because of that. It's always tunnel MPLS traffic engineering. Then we can say path, specify option here, and we'll just make this the first path option. Then we'll just specify dynamic. So I'm not going to specify the path through the network. Okay, and this right here is a really good sign. When the tunnel comes up, it's good. Tunnel doesn't come up, it's not good. You can also view it, show MPLS traffic engineering tunnels, and I'll specify. In this case, we only have one tunnel. I could specify the particular tunnel in question here. And I see that it is the administrative status is up, the operational status is up, and I am connected here. All right, so I can see that it's actually up here. Now what I can do is this tunnel has a name for it here. See it right here? This is the name of the tunnel. What I can do is I can go on. Let me go on to R1. R1 is a router in the path here. Show MPLS traffic engineering tunnel. You could specify the name and then give it the name if you want it. If you have a lot of traffic engineering tunnels configured, more than likely when you're doing a practice lab or something, you're not going to have more than one or two, maybe three traffic engineering tunnels configured here. Okay, so we see here, this is the tunnel here. Its incoming label is from this interface here. Its in labels here, and it is label number 16. So traffic coming from 3 to 5 is labeled with a label of 16. When traffic goes back, if traffic, in this case here, whatever went back out the tunnel, it would be an implicit null. But there isn't an out label. Show MPLS forwarding here. You can see here, 16 says to pop the label here. So label 16, local label 16, pop the label here. All right, so when we receive it, sorry about that. We will be expecting a label of 16 there. All right. Show MPLS, traffic engineering tunnels. See it here. All right, so it's up. It looks to be up and working. So the tunnel looks to be up and working, but what we want to do is actually send traffic down the tunnel. So let's go back to 3. Let's do a trace route to R5, trace route 150.1.5.5. So I trace routed just like I expected. I went from R3 to R1 to R5, just across the normal network. There's no traffic being routed down the tunnel. Show IP route, include. No, there's nothing that includes a tunnel interface here. So what we want to do is we want to get traffic routed down that tunnel. So what we can do is we can say IP route, and let's route R5's loopback through the tunnel. This isn't, in your normal routing and switching world, this isn't a recursive routing problem. The destination of the tunnel for a traffic engineered tunnel can be through the tunnel. And this is different than you normally see, of course, in, you normally don't route down the tunnel to, you normally don't route down a tunnel to get to the destination of the tunnel, but you could with traffic engineering. Let's just do for, in this case, there is not a tunnel on R5. So on R5 does not have a tunnel back. This is a unidirectional tunnel from R3 to R5. So what I'll do, let me just go ahead and create another loop back on here. And IP address 555.55.55.55. What I'll do is I'll advertise an OSPF so everybody has reachability, but then on R3, what I'll do is I'll route down the tunnel to get to it there. Okay, so I want to say network. And put this in area 0 here. First of all, let me make sure I can ping this here, ping 55, 55, before I start routing down the tunnel. And I can. I do a trace to it. If it was going through a label switch path in the output of the trace, you would see the labels here. Okay, so we don't see any labels here in the output of our trace route, so we're not going across a label switch path yet. Okay, so now let's route it down the tunnel. IP route 55.55.55.55. And this is tunnel 0 here. So there it is, directly connected to the tunnel. And let's do a ping. And we can ping it, and let's do a trace to it. And there it is there. It's what we expected. We saw that label 16 in the path here. So we can see it is going across the traffic engineer tunnel here. Now when it comes back, when it comes back here, let's go to 5. Trace 150.1.3.3 and source LO1, which is that new loopback here. You can see it doesn't go across the tunnel to come back. There isn't a label switch path set up from 5 to 3. Okay, 5 is the tail, 3 is the head. The traffic is set up for flowing from 3 to 5. Now we can quickly and easily do a path back if we want. If we want to have a path back here. So we'll go here and we'll specify IP unnumbered, loopback 0, tunnel mode, MPLS, traffic engineering, and then tunnel destination. Specify the destination of the tunnel, and this will be R3. And then we need to specify a path option. So that's the minimal config we need. So tunnel, MPLS, traffic engineering, path option, and 1, and just say it's dynamic. If I specified like a number like 50, it would allow me to come put a lower numbered path option in there. So what I could do is I could say, I may just put something in there saying it's a, I want to first try an explicit path. If that fails, I'm going to fall over to my dynamic path. Usually your explicit paths are of a better priority. They have a better priority than your dynamic paths. And like I said, not too many people run dynamic path selection with traffic engineering and do not manipulate that traffic engineering metric one way, shape, or form. Because it wouldn't make any sense. Because why? It could make a little sense if you want to do, if you want to create label switch paths but not use LDP, that would make sense. But you don't care which way it goes across the network. That could be one option. Because in this case, we have labels built and labels exchanged, but LDP is not running here. So MPLS, LDP, neighbor, there is no neighbor. Discovery, show MPLS, LDP, discovery. We're not even trying to discover anybody here. So this is all through RSVP. And let's go over to R3 real quick. Just verify it here. So there isn't anything there. Now what I can do is if I want the traffic to return down the tunnel, so I want it not return down the tunnel, but to come back from 5 to 3 down that other tunnel there, first thing I'm going to do is verify that it's up. Show MPLS traffic engineering tunnel. Okay, there's the first tunnel there. That's the tunnel that's going from 3 to 5. And let me see if there's another one down here. And there is. There's another one down here. And the name of the tunnel is Rack 1 R5 T0. So this tells me obviously it's Rack 1 R5, the first tunnel. Okay, and it looks like it's operational here. And let's go over to 5 and let's route down it here. What we could do actually, let's route across it through. Let's see how OSPF is going to route across if I enable OSPF to advertise that link, that tunnel. It doesn't enable OSPF on the interface. They don't become neighbors across the tunnel. It's just saying you're able to advertise. When I enable what's feature called auto route here, what it's going to do is it's going to advertise it within OSPF, but it doesn't become an interface within OSPF. So go to the tunnel, and we'll say, so tunnel, MPLS, traffic engineering, auto route, announce. So I want to announce this here. Show IP route. And I learned 3's route through the tunnel, through OSPF there. So it's learned through the tunnel here. So what we can do is let's just go over to 3 and take off that static route where we use OSPF to advertise. Well, to learn routes, the best paths through the tunnel here. You use 0. So it's tunnel, MPLS, traffic engineering, auto route, announce. See what we have here, show IP route OSPF. And we are learning routes across the tunnel. So if we switch back real quick, so let's look at this real quick here. Actually, you should have the diagram because I'm using the standard topology here. You can see that 3 goes across the tunnel. So 3 goes across the tunnel to reach 5. Okay, and 3 goes across the tunnel to reach 6, which makes sense. 3 goes across the tunnel to reach the link between 3 goes across the tunnel to reach the link between 4 and 5. Sorry, 5 and 6, and also the link between 4 and 5. 3 goes across the ATM cloud, goes from 1 to 2 to 4 to reach R4's loopback, though, in this case here. So we're not routing through. It is still not, it's not the best path for all destinations, but it is the best path for a lot of the destinations in the network here. Show IP route 150.1.5.5. So we can see it here. So the route metric is 783. The route metric, let's go look at, actually let's go back to 3 real quick. Show MPLS traffic engineering tunnels, and let's look at where it got that metric from. You can also see in here the path that we are taking, that we selected dynamically here. We can see the priority of the tunnels. Remember that the setup priority and hold priority. So MPLS traffic engineering topology is what I want to look at. Okay, so let's look down the 5 real quick. This is R3 to R1. R1 there, let's go down to 5. Here's 5 here. There's R5. There's R5's loopback. And there's this interface to R1 there. It's a available bandwidth on there is 10 megs. That's the physical bandwidth of the link. Okay, so that's R5's view of the network. So R5's view of the network, it is a 10 meg link. Let's go back to 5 real quick. Show IP route. Let's see what 5's metric is. So the route metric is 75, and it's learned across the tunnel here. So it's not taken into account that it should be 10, 64, and 1. The loopback, the Ethernet, and the serial. So it's a total of 75. So that's what its path is. So it's a path from 5 down to 3 there. If we go to 3 and look at that topology, so like my link down to 1, which is going to essentially 1 is going to get me down to R5 here, and that's essentially where we're getting this cost from here. There it is right there. So there's 3 to R1 right there, and you'll see that the traffic engineering metric is 78. And that's what we saw. Kind of hard to really look around this traffic engineering command, topology command, because there's just so much information. I mean, it's like, it's detailed information about everything that's in the network. So all the devices that are in the network and all their neighbors and all their links are in here. So it's really tough to look through. You really got to start to filter it through to find out, hey, this is really what I'm looking for, or this I'm really not looking at the right router here. Okay, so the metric it chose was based off of that interface going down to the next neighbor, that first hop in our path. The first hop in our path from R3 to R5 is across R1. That link has a OSPF cost of 780 here. All right, so now we want to see if traffic actually goes across it here. Here's the 55 network. Make sure the 55 network was in there, and it is. So we'll do a trace, 55, 55, 55, 55, and we see we went across the traffic engineering tunnel. And let's go back to R5 here, and we'll do a trace. Earlier when we traced, we just went across the network normally. And now we see we go across the traffic engineering tunnel here. So this is allowing traffic. This is allowing traffic to transit the tunnel. Now this is not a real, even though the terminology is used as a tunnel, it's not a tunnel like GRE. Essentially, it's the packet with a label attached to it. Essentially, what it is. It's whatever packet it is with a label attached to it. There's not like an MPLS tunnel, and there's an MPLS header and on this thing. It's just the labels being attached to it. That's why sometimes you'll see they'll call label switch paths LSPs. They'll say that you're setting up a tunnel. It's a tunnel, and we normally think of GRE as something something that totally encapsulates the packet, something that's on the beginning and the end of the packet. A header and a checksum on the end. So we think of that packet totally encapsulated. But with MPLS, we're just talking about the head, the beginning portion of it. So that's all we're doing is we're putting a label on that packet. The packet, if you snipped up that packet, you would just see a label, and then you would see the packet. That's all you would see. You wouldn't see any sort of strange encapsulation on it. Because if you think about it, it would just add too much overhead if you actually, tunneled the packet in there. You actually put a full encapsulation like GRE or something like that. So this isn't, an inefficient technique. You're just adding on a label. In our case, because we're going, between routers within our same core network, we really don't need MPLS. But yet, if we're trying to get traffic across a VPN between two remote VPNs, then we do need a label switch path set up for that. Okay. Now let's take it a little bit further. Let's take this a little bit further here. So we've got this basic configuration. Let's go ahead and configure traffic engineering all the way up to R6. Let me switch back real quick and switch back to my slides real quick, and let's look at what we'll do here. So what we have set up here, so we have a label switch path set up from 3 to 5. Okay, and then of course back from 5 to 3. We could bring this up here to 6, and then from that point on here, we would, if we want to do MPLS VPNs, we would configure 3 and 6 normally. So we wouldn't do anything special. We would just configure, configure our VRF, configure the our CE to PE protocol, just like you guys did earlier. But the difference would be in the core here. In the core here, what we're going to have is we're going to have a LSP set up through traffic engineering as opposed to LDP. If you're using LDP, you're going to have to rely on your IGP for the best path selection. So, or not, I guess I shouldn't say best passes, but the path you want it to select. So if you wanted to use LDP, and if you wanted to use LDP, but you wanted a path to go down through 4 and then 2 and so forth right there, you're going to have to manipulate your OSPF config. If we're just going to do traffic engineering tunnels, that's not needed. So we could have an LDP-free core network. We don't need LDP. Okay, that is not needed. We do not need LDP. We could just totally remove it. We could have MPLS VPNs working between like VPN A or VPN B. So those could be working. We could rip out LDP, throw in traffic engineering, and then nothing changes. And the only advantage we get is we get to really control the path the traffic between the VPNs take. We do not have to get in there and start manipulating our IGP metrics. What we're going to do, what we would do with MPLS traffic engineering, we're using these tunnels, What we'll do is we'll route the next hops. So the next hop across the network. So like for VP and B on R8 to get to VP and B on R7, we will route the next hop across the tunnel. So that next hop for BGP. That's the only thing we really need to route across the tunnel there. And then it lets us get in there and do some granularity to control the path the tunnel takes through the network. Okay, so let's look at a little bit more configuration. Let's look at the explicit path option here for MPLS traffic engineering. And let me share this back out real quick. Any questions up to this point here? Somebody asked a question about targeted LDP. It's really not needed for this situation. We're in a pure RSVP traffic engineering environment. We don't need LDP. So it's not needed there. There is some weird advanced configs you may see where they've got traffic engineering running in the core, then they got LDP on the edge, and then on the edge they've got the edge routers are pointing to each other for remote. They're not directly connected for remotely connecting their LDP sessions, essentially. So essentially what you're going to have is you're going to have a path on top of a path. So for some reason or another, you've got, let's say we're doing traffic engineering in R1, R5, R2, and R4, but LDP on 3 and 6. And for whatever reason or another, we want to maintain that LDP path so that not the LSP that was set up through LDP. Man, there's almost too many acronyms here. For whatever reasons, and we can put that on top of the traffic engineer if we want. Not very common, but it is possible. Really wouldn't worry about that kind of level config for the service provider or even much of the real world. Mostly it's either RSVP here, but it's mostly either RSVP or LDP, or maybe LDP on the side, totally separate. I mean, they're not tying the LDP together there. Okay, so let's share this back out here. All right. Lost my screen there. Hang on a second real quick. Okay. All right, so what we'll do is we'll enable traffic engineering all the way down to 2 and across to 4 and then back up to 5, and then we can do it up to 6 if we want. But the idea would be that we'll use an explicit path. We'll choose a path around the network here. All right, let's go down to R1. So ping 150.1.12.2, and that's the ATM. I'm not using cell mode ATM MPLS. I'm using frame mode MPLS across the ATM here. But I can ping across. Interface ATM 3/0. Let me enable it globally here. MPLS traffic engineering tunnels. OSPF1. MPLS traffic engineering area 0. MPLS traffic engineering router ID loopback 0. Usually the biggest problem problems that people run into is that just forget something small. Forget to enable traffic engineering under an interface. Forget to enable it under the routing process. It's usually one of these little small things, but yet they're not familiar with traffic engineering, so it's just, they have nowhere, they don't have any idea where to start to do your basic troubleshooting for traffic engineering. Always fall back to those basic steps that I listed earlier, those first things you do on all the routers there. Okay, so let's go to the ATM interface. Never really enabled it here, but it took IP RSVP, which say I haven't tested frame mode. I haven't tested traffic engineering across frame mode. Mostly do it with cell mode, of course. All right, but I'm just using this as a link here. Bandwidth as just a regular old link here. Okay, so that was actually already configured under R1 already had that configured under the area. I really didn't need that. I just needed it under the ATM interface there. Go to 2. So router OSPF 1, MPLS, traffic engineering, area 0. And router ID. So the global config, MPLS. Enable it globally. Let's enable it under the interfaces here. And IP RSVP bandwidth. Interface FA1/0. Let's actually do this. In the path between 1 to 4, let's make that 100 megs available. So the path from 1 to 4, let's give it 100 megs rather than 10 megs there. So back to the ATM interface, put this under here. So there's 100 megs available there for reservable bandwidth. And down to 4 here. Router OSPF1, MPLS, traffic engineering area 0. If you try to add on another area here, you see it kicks back an error. So like I said, you will see some inter-area OSPF configs, maybe from Cisco, but it's not supported in what we use. But the idea when you just put the only thing you need for inter-area traffic engineering is just need the command for the different areas on. Other than that, it's exactly the same. Okay, specify the router ID, loopback 0. Let's go into the interfaces. Actually, MPLS, traffic engineering tunnel. Then go into the interface. IP, RSVP, bandwidth. We'll say this link between 5 and 4, we'll just give it 10 megs. And the link between 4 and 2, we'll give it 100 megs. So the reservable path from 1 to 4 across 2 is 100 megs. Reservable from 1 to 4 across 5 is 10 megs. I also need to go to 5 real quick. Enable it under that interface. MPLS, traffic engineering tunnels, and IP RSVP bandwidth. 10 megs here. All right. I should be able to go over to R3 and do a show IP MPLS topology. Sorry, not show IP. Show MPLS traffic engineering topology here. And I should be able to see R4. And I do. So this shows me that this router 3 sees all the way across the network to router 4. So this is already, so this network looks like it's pretty much ready to go. We've got the basic commands on. They see each other in their topology. So now what we can do is start configuring our tunnels. What we'll do here is we'll do an explicit path, meaning we'll say 3. Let's do this. Let's make a dynamic path first between 3 and 4. And let's just see what path it chooses. Then we'll manipulate it. We'll force it to go a certain direction, the opposite of what it chose dynamically. Okay, so interface TU0. Oops, don't reuse the same tunnel. So this is I'll create a second tunnel here. IP unnumbered, LO0, tunnel destination. This is R4. And tunnel mode, MPLS, traffic engineering, and then we want to specify a path option, the tunnel, MPLS, traffic engineering, path option, and we'll make this path option 10 so it allows us to come underneath it and make a one with a lower priority, which is essentially a better priority here. And we'll just say that this is dynamic. So theoretically, this tunnel should be set up, before we look at it, it should be set up in the path that we trace route across. So trace 150.1.4.4. So we go from 3 to 1, and then 1 across the ATM, and then from 2 to 4, which makes sense. That should be the path our tunnel is set up. Show MPLS, traffic engineering, tunnel 1. And we can look at it here. This is our router. This is essentially the IP address. This is source off of here. We go down to R1. From R1, we go to R2. From R2, we go out R2's interface to R4. We go over to R4's interface, and then finally we go to R4's loopback there, just like we expected there. All right, and it chose it because that is the IGP path. The IGP path is that direction. That's what OSPF said the best path is. We said that the tunnel will be dynamic, will set itself up dynamically, so it essentially chose the same path that OSPF will select. This is why I said not too many people use dynamic unless they're somehow getting in here and manipulating the administrative weight, which is the traffic engineering metric, or they're doing explicit path. So what we're going to do is we're going to do explicit path, and we're going to route this tunnel from 3 to 1, then to 5, and then to 4, rather than the way it wants to go. So we're going to route it differently. Okay, so what we're going to need to do here is we see the path it's going now. What we want to do, IP explicit path name, and we'll say this is R3 to R4. It asks us the next address. We have to, oh, I want to put 4's address in here. I wouldn't put 4's address in here. The next address, the 4 will be the last address here. I can specify 1's loopback, which is that I have no choice but to go to 1's loopback. Let me try to go to 5's loopback here first. Then let me try to go to 4's loopback. I could also specify 5's loopback and then the interface that 5 has connected to 4. So that would pretty much ensure that it would go from 3, it has to go to 5. So it's going to go from 3 to 1. It's got to go to 5, so it goes to 5. Then I could say that the next hop in here is not the loopback of R4, but is the interface between R4 and 5, right there. So that'll ensure that it gets to 5, then 5 sends it directly the way I want it to. Because I could have a link between 5 and 2, so I say the next address is 5, and then so it goes over to 5, and then 5 sends it down to 2, and then over to 4. In this case, I'm saying I want to go to 5's loopback. I don't care how you get the 5's loopback, but then from that point on, I want to go down to 4's interface, and then I'm going to go down to 4's loopback. All right, so that's our path we have set up. Now we need to apply it here. So tunnel, MPLS, really long commands. Traffic engineering, path option. We did 10 earlier. Let's just set this one to 5. And we'll say explicit. Then it's going to ask us the name of it. And the name we chose was R3 to R4 here. All right. I like using that little arrow look there. Usually like whenever I do things like this, or whenever I do like route redistribution from connected to OSPF. I'll say connected, dash, arrow over, and then OSPF there. Show MPLS, traffic engineering tunnels, tunnel 1. Still has the other one up here. So what we're going to want to do here, let's go ahead and remove the dynamic option here. So it is aware of it here. Let's remove the dynamic option. Let's see what happens here. It went down, which we expected here. The tunnel is administratively up. The operation is down. The signaling is down. It says no address to connect to 3. No address to connect 3 to 0000. All right, so let's look at our configuration here. Let's look at what we have done so far. Obviously, that's not a very useful command. It says no address to connect to 00000. Some of the outputs of that command there. Specified 5. It didn't like that. It didn't like us skipping 1 in the path. So let's go ahead and let's go ahead and add in R1's loopback into the path here. Now we have some options in here to specify. We can see what the indexes are for here, so we can specify an index here to add, so we can delete a particular index out of here if we have a long path here. So I can say, index and then delete this index out of there if I wanted to. In this case, what I'm going to do, the simplest thing to do, just to blow it away. If you're doing real network type stuff, you do a lot of planning, you're not going to choose the lowest index number. You're going to choose some higher index numbers, so it gives you some room to put some addresses in between. So you're going to say index 10, index 20, index 30, index 40. So specify it there. But we're just going to blow it away and then put it back here. Probably is a good idea, to be safe. Go into the tunnel and take it off the tunnel. It's applied to the tunnel right now. Take it off the tunnel while it's, but since we removed it from the global configuration. So go ahead and take it off the tunnel here. You're going to save yourself a lot of headaches if you remember this kind of little stuff. Okay, so let's go back and re-enable this here, and let's put R1 here. So next address, 150.1.1.1, 150.1.5.5, and 150.1.45.4. And let me say here, and the reason I put this interface in, I put that incoming interface on R4 in there, just so that, you could have a situation, like I said, where it goes from 3 to 1 to 5, and maybe go back to 1 or something. Or at that point it's dynamic. Or I could go from 5 to 2 and then over to 4. So I want to specify that interface right there. Okay, so let's look at what we have here. Well, it actually, every time you add it in, it shows you there. So let's go back into the tunnel. Do show MPLS, traffic engineering tunnels, tunnel 1. Let's see what it says. Okay, so its operational state is down. I'm going to go ahead and shut it down while I'm under here. Let me reapply this here. So tunnel MPLS traffic engineering path option 5, explicit, and then the name here. I'm going to do a no shut here. This is where things kind of get hairy, like I said. You start making a lot of these changes here. you can start having these problems here. So let's see, show MPLS traffic engineering tunnels. Tunnel 1. Can't have too many tunnels. Okay. So it's using this path here. It's using the path, strain path here. It shows you the actual path it took. It actually shows you all the interfaces it actually took here. But that's the path we have set up here. So if we go over into a router, a midpoint router, actually, if we go down to R2 now, we should not see any more traffic engineering tunnels. Okay, it's gone now because it's rerouted itself from 3 to 1 to 5 to 4. So it's routed it itself across there. You'll find that it's a little touchy when you start making a lot of changes. You start making changes, you start changing the tunnel, you start changing the options. You know, the best thing to do was to unapply it, shut down the interface, reapply it, and then bring the interface back up. All right, so we should be able to show IP route OSPF. Let's see what routes we have here. It routes everything. In this case, it routes everything to R2. And if we go to R3, show IP route OSPF, we don't have anything for the new tunnel. We don't have any routes across this new MPLS traffic engineering tunnel that we created. So we can go under the tunnel. So tunnel, MPLS, traffic engineering, auto route, announce. So I'll announce this inside of OSPF. And I can see here now I've learned R4's loopback across that tunnel there. So if I do a trace, 50.1.4.4, and I can see that's the path I take from R1 to R5 to R4. Okay, so like I said, if we were to enable MPLS VPNs, this core wouldn't change. You would just go on and enable, configure your VRFs on your edge routers, on your PE routers, configure your BGP peering between your PE routers, configure your routing protocol between your PE and CEs, redistribute that into BGP, redistribute BGP into that protocol for the PE to CEs, and then that's it. Everything else would be done. Okay, let me step back. That's not it. You would need to announce the routes for those next hops for BGP through the tunnel. Either do a static, you do a policy, or you auto-announce it. Okay, in this case here, in our case here, we're actually adding a little bit of overhead onto this here. We have a little bit of overhead here because we're adding a label on, even though it's really not needed. But once we get into those VPNs, it will be needed. Someone had a question. Let me send it real quick, and I'll pop my screen back up. So that question, is it the tunnel destination that it makes it use of the tunnel when you enable the auto route announce? Yes, correct. That's what we saw here. We could see that the destination of the tunnel was routed through the tunnel there. Show IP route OSPF. The other side will not have a route through the tunnel because it's unidirectional. So it's only the local side there. So it's only the local side there that's going to have the side that has the tunnel head will have the routes down the tunnel. If I want to come back through a tunnel from 4 to 3, I'm going to have to obviously configure that. See what any other routes we have going down that tunnel. blue tunnel. No, that's the only one that loop back. Everything else is preferring. Everything else is preferring the outside, means the non-label switch path, so directly through there. What we can do is we could go in here and manipulate this so that it starts preferring. You know, if we look at, okay, how does R3 get to the link between R4 and 5? 150.1. Oh, it goes across this tunnel here. Let's flirt with danger and let's make it go across the other tunnel. Right now it's going to get to the link between 4 and 5. For 3 to get to the link between 4 and 5, 3 is going to 5 through here. What I want to do is I want 3 to go to 4 to get to the link between 4 and 5. Okay. Here's where the class starts to fall apart. Start to deviate from the standard plan. All right, tunnel, MPLS, traffic engineering. And what I want to say is auto route, metric, and specify the metric here. And I will give this this is under, see what interface, this is the first tunnel interface. We'll try to make this less attractive. Set metrics for auto routes. Try something like 5,000. So let's see what happens. All right, so we're not preferring, so we lost that tunnel. Everything else should now go outside the tunnel because the non-label switch path is a lower metric. Over here real quick. Okay. So they're going outside of the tunnel here because obviously the tunnel's got a cost of 5,000. Obviously that's higher than the non-label switch path metric here. So what we want to do is we want to make 4. We want to go here and make that other tunnel to 4, the second tunnel now, the preferred here. And let's see if we can do that. It's going to be an easy one here, int. Let's give its metric 1. The 1 here. Oh, there it goes. Now we're routing through the tunnel. So now we have routes through the tunnel here. Because by default, it received the metric based off of OSPF. OSPF's metric became the traffic engineering metric. So the cost across that tunnel was just the cost from R3 to get to R1. It's your outgoing interface, essentially. So it was 700 and change here. All right, and we can see here, like on the path to R4, it's a cost of 2. It's the cost of 1 we put on the tunnel, and a cost of 1 for R4's loopback. Here's 12 here. This is the it's an Ethernet. It looks like an Ethernet interface and a loopback, and then the tunnel itself there. So let's do a trace. If the trace doesn't work, we'll just end the class now. Just kidding. It's working across. Okay, and let's go to 2. Let's see how he routes to 2. How 3 routes to 2. Goes a long way. So it goes across the tunnel down to R4. It goes across the tunnel down to R4 there. Okay, so we end up with some suboptimal routing, but you know it may look like suboptimal routing. Trace to R6. Trace. Someone asked to trace to R6 here. and that's the long way around. Goes from 1 to 5. Sorry, yeah, it goes from 3, 1, 5, 4, 2, 1, 5, 6. So you're getting full utilization of the network. You're going across every possible router in your core. All right, you're getting your money's worth. It does, because when 4 gets down here, show IP route 150.1.6.6. When 4 goes to 6, the best path is to go across the Ethernet, the ATM, the FAST-E, and then the GIGI over going across the T1 there, the serial interface there. All right, but you affect this path here. Now, we can get in here and manipulate the path so that, you know, that the tunnel goes from 3 to 1 to 2 to 4, and then, you know, so the traffic when we trace to 6 from 3, it would go from 3 to 1 to 2 to 4, back to 2, back to 1 to 5, then to 6. I mean, it's really a long way around. All right. So it's whatever, you know, whatever we whatever we want to have here. Let me do one more thing real quick. So before we end here for the day, if we were going to run MPLS VPNs between 3 and 6, so if we were going to run MPLS VPNs between 3 and 6 here, on 3 and 6 here, we'll create our, so we'll say neighbor 150.1, this is on 3, 6.6, remote AS 200, update source, loopback 0, and then we could say no, we could deactivate the neighbor, no neighbor 150, or do the default there. Activate, and address family VPN, activate the neighbor here. And let's go down to 6 real quick. 150.1.3.3, source LO0. Definitely something you want to do before you start bringing up BGP. 200, neighbor 150.1.3.3, remote AS 200, update source loopback 0, and address family IPv4. It's complaining that the capabilities aren't supported because I don't have VPN v4 enabled yet. Neighbor 150.1.3.3, activate, and do a no on it for IPv4. Address family VPN, and I will do VPN support here. Okay, this should come up here. Let's see if it does come up. Show MPLS, show IP, BGP, VPN. What's up? Just took a second there. All right. So now it's actually up, show IP. Now if I put the VRFB, RD, it's just for simplicity's sake, make it something simple. Route target, both. And this will be 3636, just for simplicity's sake here. Interface G0/1, IP VRF forwarding. Before I do the forwarding, I like to do a show run int. Then I can just grab this off here and then paste it in. IP VRF forwarding B. apply that back here. Router BGP 200, address family IPv4, BRF, B. It is case sensitive too. I think Brian mentioned that. Redistribute, connected. Going to bring in that interface there. Let's go to 3 here. IPVRF, B, route descriptor, 3:3 here. Route target, both 3636. What I used up there, correct? Scroll up to make 100% sure. Yeah, I did, 3636. And go into the interface here, and this is interface E0/1. Do show run int E0/1. Actually, it would probably have been easier for me to actually type that command, right, IP address, than type the show run interface 0 include IP address. All right, IPVRF forwarding B, and apply this IP address here. Router BGP 200, IPv4, BRF, B, redistribute, connected. All right, show IP, BGP, DP4, all summary. Should see one route, which I do. A routing table, that's the directly connected interfaces here. The next hop, 6. 6 is loopback here. And let's go over to 6 real quick here. Show IP, BGP. One of the commands you will type a lot is that command. Show IP, BGP, VPNv4, all VRFs, summary. And show IP route VRF B. As a side note, when you're practicing doing MPLS VPNs, try to make your VPN name something simple. Don't make them something really long. When, like our backbone config for the SP racks, we only have one backbone router. They're all, it's doing VRFs. At first, I had them really long, like backbone 1, rack 1, or something, underscore rack 1. It just took forever to do a show command on anything with that. I like doing something that's very simple. Okay, so there's our basic MPLS VPN configured. Let's do a ping BRFB 10.1.37.3. Address, let's see here. Oh, that's not going to work, right? Show MPLS forwarding. We don't have traffic engineering. It gets untagged. When it's untagged, something's wrong. So to get to that next hop, right here, it's untagged. It does not have. It's it's essentially it doesn't have a label associated with it, essentially. So what we're going to do is we're going to create a tunnel between 3 and 6. So we'll create a traffic and engineering tunnel between 3 and 6, and then 1, of course, back, so that we can use 3 and 6 to distribute the labels. Okay, so router OSPF 1, MPLS traffic engineering area 0. And for this, for these configs, you pretty much have to get into the habit of trying to remember the basic configuration. You can memorize the basic configuration. It'll be a lot easier for you when you get into the lab. If you can't even do the basic configuration, you have a lot ahead of you. Not that you can't look it up, but it's just a lot easier if you have the basic configuration memorized, like those basic steps I showed in the slides there. So, so it's enabled here, MPLS, traffic engineering tunnels. And let's go ahead and under the interface here, gigabit 0/0, IP, RSVP bandwidth. And let's go to 5 and enable on 5's interface to R6. Then when I go over to R3, I should be able to do a show MPLS, traffic engineering topology, R6's router ID, and I should be able to see it in there. If I don't see it in there, that means something's broken somewhere in the path. That means you need to, if something's broken somewhere in the path, that means you need to fix something somewhere in the path. Good troubleshooting, huh? If you can't ping, something's broken somewhere. So fix something somewhere. All right. And MPLS, traffic engineering tunnels, MPLS, traffic engineering. IP. I always want to put, I don't know, traffic. I want to specify the bandwidth through traffic engineering. Bandwidth. Okay. Should come up pretty quick. Show MPLS, traffic engineering, topology, 50.1.6.6, and it's there. Okay, so it looks like it's up. I'll bring up a tunnel, int tu2, IP unnumbered, LO0, tunnel destination, 150.1.6.6. Of course, we're going to have to do one back, obviously, here. And tunnel mode, MPLS, traffic engineering, and tunnel MPLS, traffic engineering, path option, 1, dynamic. I think if they tried, they'd have a hard time making these commands any longer. Auto route, announce. Because what I want to do, I want to ensure that 6 goes across the tunnel to reach 3. And 3 goes across the tunnel to reach 6. So that's why I'm going to go ahead and announce it in there so they get those loopbacks in there. All right. So let's look at the configuration here. Now, one thing I didn't do is I never specified a bandwidth. Now, I could go into the tunnel and say that my bandwidth for this tunnel, I want at least you know, 1 mega bandwidth. Okay, so I want at least 1 mega bandwidth here. It depends, you know, it just depends on what I want. That part of the configuration I don't spend a lot of time on because it's pretty straightforward. You either want this bandwidth or you don't want this bandwidth. And if you want this bandwidth, you need to make sure that your IPRSD bandwidth command is larger than what you're trying to reserve. If it's not, you're going to have a limitation to the amount of tunnels or any tunnels that can be brought up. Okay, but I didn't specify it in there. Okay, I put it in here now for this one just to show you here. Also, the The options for the priorities. Here, I could say the setup priority for this one is 0, and the hold priority is also 0. What this would mean is that I would preempt the other tunnels. Their setup priority is going to be 7, and then a hold 0. Okay, well, their hold is the same thing, so I should take it back. I have a higher priority to get set up, but I don't have a higher priority to take them back down because their priority is the same thing as me. All right. And as a side note, it's usually not good when your tunnel goes down all of a sudden like this. Not what you want to see. You want it to be up, and you want it to stay up. All right. So we're going to have to look at that in a second here. Show MPLS, traffic engineering tunnels, tunnel 2. It's up. Its operational mode is down. Path is not valid. Go to 1. I go to 1, and then I go to 5. I go to 5, explicit route here. No path to destination. Let's see here. But it doesn't mean I don't, I can't ping that destination. Well, as long as you can type the destination, type ping. So it doesn't mean I can't ping it when it says there's no path. It means somewhere in the path something's broken. Okay, something's broken somewhere in this path here. Show IP route 150.1.6.6. And let's look at the route here real quick here. It's known via the tunnel 1. So we can see we've got problems. We've got tunnels trying to route inside of tunnels. So really what we want to do for this scenario, because we built something really messed up earlier, let's just shut down those tunnels. We don't want tunnels, obviously. We would configure our network so that tunnels aren't routing inside of other tunnels. So let's just shut down this tunnel. Shut down the other tunnel, because we're using tunnel 2. Let's look at it here. Okay, let's see if this tunnel will bring itself back up. I'm going to bounce it. We're almost done here. No, we're running a little bit late. Sometimes when I bounce it like that, you notice it never gave me that down. Administratively down. Let me bounce it and hold on a second. Wait till it gives me the administrative down. Now I'll do a no shut. Cisco routers can be pretty sneaky sometimes. They're not sure if you really meant to shut down that interface. All right, let's go to 5. Shut down its tunnel 2. Let's take these tunnels out of the picture here. All right, let's go back to 3. Still routing across the 0 there. Let me look at my tunnel. Path is down and it says it's not valid. Some of the reasons it could not be valid, maybe there's not enough bandwidth. Maybe there's already tunnels set up that are taking up all the available bandwidth. So let's take out those optional commands. The idea is that you're going to peel back your config to a minimal config to get it working, and then once it's working, you can go there and start doing some fine-tuning of your bandwidth and your priorities and so forth there. See, as soon as I did that, so something's wrong somewhere. You see that? Take off those options, get back to that basic tunnel, get it to come up. Something was wrong with that option. Maybe the other tunnels were already set up. They already reserved the bandwidth, even though they weren't asking for any bandwidth. Take them off, get it back working with a basic tunnel, and then see what happens. Show IP route 150.1.6.6. Now it's learned via the tunnel. Now I'm going to do it back the other way now. Lint TU 0, IP unnumbered, LO 0, 2 ends in unnumbered. Tunnel destination 150.1.3.3. Tunnel mode MPLS traffic engineering, because you're telling it not to do GRE or whatever there. And tunnel MPLS traffic engineering path option 1 dynamic. And also I'm going to do auto route announce. Okay, so I should have the route through the tunnel here. Show IP route 150.1.3.3, and I do. Show MPLS forwarding. I popped the tag going to 3. This is not what we saw earlier. We saw untagged earlier. So I popped the tag and send it out the tunnel. All right, and let's go to 3. Show MPLS forwarding. All right, just on the output of this one command, you can tell if you're going to pass the CCA lab or not. If it all says untagged, your network's not going to work. You want it to say pop tag or some sort of have some sort of label value there. Let's go in the middle here. Let's go to 2. Show MPLS forwarding 150.1.6.6. We don't have anything in the middle here. Let's do a show MPLS forwarding. Nothing here. Let's go ahead and go back to 6 now. Let's look at the routing table. So it shows that this is up. And as Brian showed you guys earlier, as he showed you earlier, sometimes though this can be can take a little bit of time to converge. All right, let's look at. So this is up here. And then I can ping from BRF all the way across. So I do a trace, and then I can specify VRF here, B1, and I want to trace to 10.1.37.3. So you can see here, I go to 5 to 1. You can see it's a stack label here. There's the VPN label there. This is what you want to do before you start configuring those CE devices. Make sure you have reachability between the PEs within those interfaces in the VRF. Once you have that, then you can go on and add your additional configuration. So I can go on now to 7 and just say IP route 000000000 10.1.37.3. Put the same thing on the other router here. Or if I wanted to, I could enable a routing protocol. Ping. Let me make sure I can ping. Okay, I can ping there. To go back. Oops. Go to 8 real quick. IP routing and 10.1.68.6. We're going to do a ping 10.1.68.6. Okay, I can ping. Now I want to see if I can ping all the way across. So I want to ping 10.1.37.3. And I can ping 3. That means I can ping the other PE router. Let me see if I can ping R7. And I can ping all the way across. So this shows me it's working. It's going through the traffic engineer tunnel. The biggest thing you want to ensure is that you are routing that BGP next hop through the tunnel. That's the biggest thing. Someone had a question. They said, shouldn't it show 1 hop for trace route? Not by default. When we get into some advanced features, we'll show you how to make it look like 1 hop. But right now, the MPLS network is exposed. I mean, it's going to, when you trace right across, you're going to see all the routers there. See it here? So we're seeing all the routers in the path there. There is some things when we get, we'll talk about that if we want to hide the MPLS network from, these devices here. So this doesn't show up when you do a trace route across the network, which is actually quite common. Not to set it up to have it not to do respond to trace routes there. All right. So the configuration, as you see here, from this point on, we go to 6. This is the standard MPLS VPNs. Got my route target, got my route descriptor. Here, I go down to my BGP config here. Scroll up real quick here. There's my VRF. Of course, I'm peering here. There's my VRF. I'm redistributing it connected in, so I get that connected route there. And then up to my traffic engineering tunnel. And there I have it there. Traffic engineering tunnel, IPN number loopback 0, tunnel destination, and it's enabled there. Yeah, if you guys want this configuration, I can save this configuration for you. If anybody wants it here. It's actually, to be honest with you, I mean, there's not a lot of examples that show traffic engineering really working for label distribution. You see a lot of people talk about it, oh, yep, you can do label distribution through RSVP. Yep, it's one of the protocols, but you really don't see it out there. But I'll save these configs so that we can get them posted up there in that file section there. We had some little bit of trouble earlier. We had a little bit of trouble earlier because we had tunnels routing inside of tunnels, which isn't very good. But once we got that fixed and got it cleaned up, everything was working. Now we could get in there and do some traffic engineering, put an explicit path in. Once you have this config I give you, if you take this config, you can do a lot of manipulation to it, get in there and let it reserve different bandwidth or whatever there, or create another tunnel between 3 and 6, or create a tunnel between 5 and 1 or whatever there, and have it reserve more of the bandwidth, and then see if there's any bandwidth available there. But you can use this as a basic template to learn basic traffic engineering with MPLS VPNs. Because personally, like I said, from what I see out there, I see a lot of examples of MPLS VPNs using LDP, MPLS VPNs using a little bit of BGP for inter-AS stuff, but you just don't see a lot of pure traffic engineering. When you get in the workbook, you will see some pure traffic engineering. All right, but this config that we'll post up for you guys will have the initial configs that you can lay in, and then you can get in there and start doing all the advanced stuff with traffic engineering. And there's a lot of stuff with traffic engineering that's just way beyond the scope. That's just way beyond the scope of the lab and beyond the operating system, the iOS, what it supports there. All right. Like I said, that should get everybody here. Usually there's a lot of, not usually, but there's a lot of obscure topics with traffic engineering. And if you have, questions about some of the, more advanced configs that really don't relate to the SP Lab because they're not supported on the platforms here, the MPLS traffic engineering book is definitely a good book. Talks about fast reroute. What fast reroute does essentially pre-builds additional tunnels so that if your primary tunnel goes down, you can route around it. So let's say if you have a tunnel set up between 6 and 3 and it goes across from 6, 5 to 1 to 3, you can have a backup tunnel that goes 6, 5, 4, 2, 1, and then 3. And then it could switch over real quick without any real notice of the problem of the outage to the customers who are using that traffic engineering, your traffic engineering configuration there. Okay. Okay, so we'll go ahead. We don't support A couple people have asked about doing fast reroute, but it's not supported in the iOS that you're going to be tested on there. Okay, on Friday afternoon, if anybody wants to go over, Friday we'll have a little bit extra time. If anybody wants to go over some of the more advanced features of traffic engineering that really aren't covered, really don't relate to the SP lab and the iOS versions that we're using, I'll gladly answer your questions then. I can show you some configurations for fast reroute, but even if we load them on VXRs, we won't be able to get it to work unless we switch over to 12.0. But I'll show you some advanced configs. Some people are asking about the affinity and some other things you can do as far as QoS for traffic engineering tunnels. On Friday afternoon, this will also be recorded. I'll go ahead and answer those types of questions then, because it's really it's kind of late now, and it's really beyond the scope of what we need to cover here. This is really advanced. Let me tell you what. This is really advanced what we did today. This configuration with MPLS VPNs, this is pretty advanced for traffic engineering. The rest of the stuff is simple. The rest of the stuff is just you fine-tuning traffic engineering. You going in there manipulating the bandwidth. You go and manipulate the priorities and those kind of things. This is the hard part, getting it actually working and understanding it. Okay, so we'll go ahead and end here for the day. Like I said, on Friday, if you guys have any particular feature you'd like to go over, we can go over them there.